My title initially was just this stuff in blue, but then I thought to add a couple of more things because I thought that might be interesting. Let's see if we can make it. But I'm going to start by discussing the process tensor again, that Gerald did a great job describing. I'm going to take a slightly different approach to give a different context for what the process tensor is and how we came upon it. So let's start with stochastic processes, and feel free to interrupt anytime. So stochastic processes. Classically, a stochastic process is, so let's say you have some stock that has, you want to invest in it, and you might expect it to do something over the next few days. So it might take two possible trajectories of many, and you might assign a probability to it. And that is the idea of a stochastic process, is the joint probability distribution of some random variable, could be the price of a stock, over time. So it's a multi-time distribution. So it's not a distribution for on what it might be on Monday, and then what it might be on Tuesday, and so on. It is really a joint distribution over multiple times. Now, it has certain properties. One of the nice properties a probability distribution has, that suppose you don't care about the price of the stock on Wednesday because you're going to take the day off and go to the beach, then you can simply average the distribution over that particular day. And by averaging, you sum over that date, the kth day here, and you just cancel out and you get the distribution over the remaining days. The reason I mention this is because that turns out to be a crucial problem when you try to generalize this idea to quantum mechanics. So there's a notion of Kolmogorov extension theorem to formally define the stochastic process through this. So we can always go from a larger distribution to smaller distribution. So we can think of a 2-point probability distribution will be contained in 3-point probability distribution, would be contained in 4-point probability distribution. So if these are the family of all 2-point distributions, then this hierarchy exists. And what Kolmogorov proved was that there is a continuous probability distribution, and that is the stochastic process. And what we see in world when we observe smoke, doing random walk, smoke particles doing a random walk, or birds flying around outside because you're bored by the talk, those are stochastic processes. You're sampling from this continuous distribution. Now, there are some nice properties it has. We could have an instance where we might have two possible trajectories over the next few time steps, and then the price of the stock goes to some particular value on both of these trajectories. And now we might want to ask, where does it go next? Does it go up or go down? And that may depend on whether the red trajectory was realized or the blue trajectory was realized. And that is that is the idea that the history matters, and that's non-Markovianity. Right? So classically, this is well defined. In quantum, people have argued, although it's still well defined, and we'll get to that in a bit. Markovian processes are ones where we don't care. We only care about the current price, and the future does not depend on the past. And the other thing that is widely studied is the master equation, where you have some time derivative of probability distribution related to some objects that drives that derivative. Now, there's a nice relationship with all of these objects with the Kolmogorov extension theorem, or the hierarchy of probability distributions. Markovian processes are ones contained in all are contained by 2-point probability distributions. So if you're guaranteed a Markovian process, then you only need to know this in order to know the rest. You can get everything else from that. Master equations, suppose you have a process and you want to construct a master equation by observing the process, you can do that by only looking at 3-point correlation functions, at least generic master equations that we're used to. And non-Markovian, depending on how many correlations you want to look at, requires some endpoint probability distribution. In practice, n tends not to be very large, and that's why in practice we tend to like master equations, because 3 points is pretty good. Usually you don't want to spend too much time looking at higher and higher order correlations. But for some problems, it becomes important, and we'll go over those. Okay, so how do we make this into something quantum? Well, one way to do things is you take a probability distribution and you turn that into a density matrix. That's a common way to take something stochastic classically and turn it into a quantum object. We can do that. Say we have a probability distribution of 3 coins that may be correlated. We can turn that into 3 qubits that may be correlated. So this is a kind of a conceptual generalization. The objects on the right-hand side are more general than the objects on the left-hand side. These could be entangled and could also contain classical correlations. So then our goal for a stochastic process should be to take a multi-time probability distribution and turn that into a multi-time density matrix. And that's what the process tensor is. And we'll get to that in a minute. So that's the goal. So how do we do it? Well, as Gerald showed yesterday, that the most general quantum process we might imagine, we have a system and we have an environment. We can't touch the environment, we can't see it, so we can only touch the system. We can relax that in many applications, as a lot of the talks alluded yesterday, but we have a system and we might do things to the system. That's denoted by these blue boxes. Those are control operations. Usually they're represented by completely positive maps. They're also known as instruments. There could be measurements, there could be unitaries, could be something in between, so on. And the X's are the outcomes of those measurements, and there could be null outcomes. So if you apply a unitary, there is no outcome corresponding to it, but you might keep a record of what unitary you applied. And T's are the times. So now if you were to make a bunch of measurements and observe some sequence of outcomes, we will get a probability distribution for seeing those outcomes. And we might make a measurement at the end to turn this sequence into a probability distribution. Now the question is this a definition of a quantum stochastic process? Could this be a way to describe quantum stochastic process? Because this right here is a classical stochastic process. This is nothing more than some notion of Born rule. The answer is no. And here's the reason. Let's imagine we do an experiment, and I actually don't care about what happens at time step 1. So classically, I could just sum over all possible outcomes at that time step 1. So I might run a sequence of experiments where I do something at time step 1, but I just average over all of the outcomes. Is that the same as not doing anything at time step 1? So imagine you're doing a Stern-Gerlach experiment. You do a X measurement, a Z measurement, an X measurement, something like that. Now, suppose you skip the intermediate Z measurement. Is that the same? And the answer is no. And one of the reasons for that is a distinction between classical stochastic process and quantum stochastic processes. You could sit here and watch birds without disturbing them. You just can't do that in quantum mechanics. Anytime you make an observation, anytime you interact with the system, you affected. And you have to account for the things that you do to the system and separate that out from what the universe does to the system. That's the challenge. Now, this is particularly bad if we can't come up with a consistent definition of a stochastic process. This becomes problematic. First of all, Kolmogorov extension theorem has broken down. We can't define a continuous process from which all of these things come out as marginals. Marginalization doesn't work. So we'll have to have infinite possible classical stochastic processes to describe a single quantum stochastic process. So how do we get around that? Well, there's a simple way. You do nothing. You take the blue boxes and you move them down. Right? So I've done nothing. I've just moved those blue boxes down. And then you take a crayon, take 2 crayons, and you color the top thing in red, and you color the bottom thing in blue. Now, this audience is going to be perfect for this. I don't have to tell anyone that these are tensors, right? I often struggle to convince people that these are nothing more than just multi-index matrices or tensors. So this is nothing more than contraction of a tensor up top and, a tensor up top and this tensor with this tensor. So we just have to list them separately. Well, what is this tensor? Well, that's the stuff that you don't know anything about. That's the system environment interaction, initial state you might not know anything about. This is all the stuff you can control. Right? So this is in your possession. This is entirely your control. This is that stuff that you cannot control. So this is what we're going to call the process. So that's the idea of process tensor. It describes a quantum process, and it's a tensor. Hence the name process tensor, not very creative. We debated a billion other names, but came up with that. I don't know why. And the blue tensor is a control tensor. Now, this has a very nice interpretation, a couple of nice interpretations. So the line up above of the environment, that is the non-Markovian memory. The line below in the blue is a feed-forward control. So anytime you observe a process, and depending on what you observe, you might change the way you interact with the process. That is memory that you're carrying in your apparatus. But probably the most remarkable thing here is how these 2 tensors contract with each other. It's really as simple as that. There's probably a transpose missing, but never mind. We've got an object, upsilon, the process tensor, has some really nice properties. One can show that it's positive. It's got unit trace, and it's Hermitian. Yeah.
So, okay, just work. Can you remind me the definition of positiveness for a tensor with many indices?
That's
for matrix, yes.
That's a good question. So it's completely positive. This is actually okay, because this is a density matrix representation. So what does it mean that is positive or completely positive? You can think of this as a density matrix, and then you can just look at its eigenvalues for 1. But you can ask the question, suppose I apply, so the A's are instruments, so suppose I apply completely positive transformations here, then everything that comes out here will also be positive. So it preserves positivity. A can, if it's an instrument or if it's a sequence of measurements, it's also a positive object, but it's a trace non-increasing object. But A could be more general. It could be an observable. It could be a bunch of sigma z operators, right? You might measuring sigma z expectation values over and over and over, or something like that. Right? That need not be a positive object. So computing the expectation value of that observable that you get to choose is nothing more than you take the density matrix, the multi-time density matrix, and you take the trace of your observable with it. And that is known as the Born rule, right? That's nothing more than usual quantum mechanics. Usual quantum mechanics we do in space. This is in time or in space-time. So it's just quantum mechanics extended to space-time. Nothing terribly, nothing changes here. Okay, and that answers the question, right? So this density matrix is a multi-time density matrix of a single system. Sorry. If you look at the legs of that process, let's go back a slide. If I look at the legs of this process, all of these legs have dimensionality of the system. The environment dimensionality is hidden in here. So it is exactly the density matrix of a system across many times. There's a factor of 2. So if I have a endpoint correlation of a bit in classical, then the dimensionality of it is 2 to the n. Here you get 2 to the 2n. There's an extra factor of 2, and that's because each of these legs is a density matrix on its own. And you get a pair for every time step. Okay. So now with this, you can prove the Kolmogorov extension theorem. So you can start with some process tensor, and marginalization is well defined, so that I can start with a 13-step process tensor, and I can get all possible 8-step process tensors from it. I can get 5-step process tensors from that, and I can get the whole family. I just simply have to insert the identity transformation in the empty slots. And you get that whole hierarchy. And then you can prove the existence of a continuous quantum process that contains the hierarchy. And you get the same statement. You get completely positive maps here. You get quantum states here. These are nothing more than quantum states at a given time. No time, i.e., there's no time evolution. These are 2-point correlation functions, i.e., CP-TP maps, and master equations can be any Nakashima-Swanzig master equation can be constructed with a family of 3-point process tensors. We formally show that in this paper. And this generalized extension theorem implies Kolmogorov's extension theorem. So it actually works in the same way and captures non-commuting things as well. This is a different way to think about it. Remember the trajectories of the stock prices. You can think about trajectories of quantum amplitudes in a given basis. So a quantum stochastic process can be then defined as a family of amplitudes as opposed to probabilities for a basis trajectories, which can then interfere. Okay, so how good is this? Any open quantum evolution can be described as that. It's linear, it's completely positive, so the usual problems of complete positivity are gone. And this is sort of how I got onto this business, because Pachuca's famous paper about giving up complete positivity and so on in the 90s, just there were issues, and this is the way to do it. You can do tomography here by just varying the control, so you can actually reconstruct this in lab, and we've done that, and I'll report those results. And this is described in language of quantum combs. So quantum combs is a general architecture that some folks in Pavia came up with about 15 years ago. They use it for a variety of foundational things, including when there is no causal order, and folks in Vienna work on this. And there's a huge industry of all sorts of interesting physics that one can do here. So this is another application. It turns out that these ideas were explored by Lindblad in 1979 in pretty much the same language. We just didn't know it. No one else seems to have read that paper because it has very few citations. But Lindblad basically had the whole thing. And then he kind of shoved it away and never worked on it. That's not entirely true. He did some really interesting work with it. Okay. Now, this gives us a nice interpretation of Markovianity, non-Markovianity in quantum physics. So, so to answer your complete positivity question again a little bit more formally, if you have a process here and you stick in a bunch of positive objects on each of the slots with some memory, i.e., let's say pure maximally entangled states, then the object you get here is always going to be positive. If you choose maximally entangled states, then you get the Choi representation. So that's the density matrix form formally. Now you can write that as a matrix product operator that looks like that. And the black line going through it is exactly the non-Markovian memory. If you erase that, i.e., one way you can do that is by just writing down the tensor product of these marginals, then you can define a measure of non-Markovianity and so on. And this is a multi-time non-Markovianity. And there are, as Gerald talked about yesterday, there are Lindblad processes that will have non-Markovian memory. This was also known to Lindblad in 1980 in a manuscript that was unpublished and not to be found anywhere, except when he passed away last November. Ingmar Bengtsson has been going through his papers and whatever he has, and he found it, and he's recently shared it with a few of us. So if you want a copy, so I mean, it's kind of remarkable how much he already knew, and kind of was ignored for 20 years, 30 years. Okay, what do we do with it? Should keep an eye on time. Good, I think I'm all right. So we can think of something called many-time physics now, right? So there's this notion of many-body physics. We can have quantum states of lots of qubits, and a lot of you work on that. And we have a whole hierarchy of things here. So we have spatially entangled states. We have some states that have nice tensor network representation because they don't have a lot of entanglement, so they're classically tractable. And then we have also separable states. Well, these things are nothing more than density matrices. Modulo, they have certain causality conditions that I haven't really talked about, but effectively what it says is that you can't affect the past with some choices in the future. If you give up some causal order, you can do that. You can do you can have a causal version of Wheeler's delayed choice experiment, for instance. But in ordered combs, you can't do that. So then these things form a set which have things like temporally entangled processes. You can also have bounded causal structures. In other words, causal structures that don't have a huge amount of entanglement, and you can describe them with tensor networks and other techniques. And you guys know way more about that than I do.
Is entanglement the word for it?
Yeah. Sorry, who was that? Marlon. Yeah. Well, yes. Loosely speaking.
Yeah.
Now, why loosely speaking? So because these have same representation as states, there is the usual notion of entanglement. Now, there are processes that are separable that cannot be classically attained. But actually, we also have that in the state theory, right? The hierarchy of a resource theory of entanglement contains separable operations, separability preserving operations, things like the tile state. So that whole complexity between purely entangled and purely separable also exists here.
I agree, but now you're talking about correlations that go in time, not in space.
Yep. So you can't do anything like Bell, if that's what you're worried about, for the reason that Bell type inequalities assume there are no signaling theories. Signaling is allowed, but you can do something exotic that where causality replaces the no signaling structure. So you get just as much richness. Well, it's to be determined. People are working on that. That's That's the stuff that Vienna crew does. So they have this notion of causal separability or causal inseparability, which looks just like the CH-SH game or the CH game, whichever one it is.
So how is this related to the consistent histories of books
By Griffith.
Yeah.
That's a good question. I've looked into it. I think it's roughly the same.
Okay.
I think this is a bit cleaner, at least for me. But it's roughly the same, but not identical. I think they don't have the full family of control and so on.
I see. So but if you read Griffith's book, then it actually talks about all the tensor history.
Yeah.
Tensors, and then
Yeah.
the main thing is about the competitive.
So we don't worry about any of those foundational things. We just want to get the structure right. But it's coming from a very similar spirit. Yeah. And Marlon, to answer one more, to further answer your question, entanglement has an operational meaning. So if I have a channel, multi-time channel with that has entanglement, that means I can take a unentangled state of say 4-partite unentangled state and map it into a 4-partite entangled state, could be genuinely multi-partite entangled state, if that process has genuine multi-partite entangled structure. So it is a channel that gives you entanglement. If it's separable, then it will kill all entanglement. So it has very clean operational meaning. Okay, so what can we do with it? Well, there is a lot. I sort of talked about the stuff about causality and structure. I won't talk about that so much. The three things that my group works on are, the way I like to think about it is, usually in complexity, you have these notions that you have things that are simple and has low complexity, and then things that are too complex so that it has low complexity, i.e. you can describe it statistically without having to worry too much about it. And then in middle, somehow it peaks. And you have something very similar. So quantum computers, they're pretty good devices. They have low quantum memory. It is quantum, but it doesn't have a huge amount of complexity. You have things like FMO and other exotic processes that various folks talked about yesterday. That is going to be somewhere in the middle. High complexity, takes effort to describe it. And then you have things like chaos. It's so complex that you'll get no memory. So I'll talk about three of these. Let's start with chaos real quick. And with chaos, I'm not going to spend too much time on it, but I just kind of want to report this result. So look, the literature in quantum chaos goes back 50 years. And there are a lot of hangups there, right? And some people will say there's no such thing as quantum chaos because quantum mechanics is linear. And at the same time, you know that there is quantum chaos because you see a strong signature. So the question we wanted to ask, we started with Lorentz's famous quote, we want something small leading to something big, right? That's all we want. So let's forget about the dogma, the mathematical dogma of chaos, and we'll just start with this. So we set up the problem like this. So we have a process tensor here, a butterfly, something small, maybe 1 qubit, is doing something, is fluttering its wings. The environment could be lots of qubits, could be 1 million qubits. And I take a second copy of that, and the butterfly doing something else, flutters its wing in a different way. And I want to compare what happens to the whole state. So I want the different flutters to lead to different states for the whole at the end. But I want the differences to be stark. So imagine over here, I also get a nice sunny day with same cloud, but there's a little bit of gray cloud sitting next to it. Technically, these two things are orthogonal, right? That gray cloud is noticeably different. but I really want them to be starkly different. I want this to be a tornado. I want this to be a nice, happy, fluffy cloud day. So that's the demand, right? And the rest of it is quantum mechanics, and I'll skip the details. It requires a little bit of tensor network, nothing terribly sophisticated. And what we find, actually what we find is listed here. We find that quantum chaos equals spatial temporal volume entanglement. So which is the spatial part? This is space. This is the time part. So we get volume entanglement between all of these open legs, if I were to leave these legs open and not commit to a particular butterfly. So I won't go into those details, but it actually, now one might say that who cares? That's a choice, a definition. But it turns out that this is consistent with things like Low-Schmidt echo. Perez defined this, Low-Schmidt talked about this 100 years ago, 50 years ago, something like that. It's consistent with dynamical entropy, the notion of chaos by Sinai and Kolmogorov from the 50s. It's consistent with things like autark and local operator entanglement. In fact, what we actually show is that this is more consistent with local operator entanglement, and autark is a specific realization of LOE. In fact, it's stronger than all of these. So all of these things can have false positives, except for local operator entanglement, potentially. They're still open, we still haven't fully resolved that, but autarks can certainly have false positives. Both of these can have false positives. And in fact, Lindblad worked on this, and he found a false positive and claimed that it turns out that chaos doesn't have to have complex level spacing statistics. He reached the wrong conclusion. And we can show, so these are the ways that people look at chaos. This is the entanglement structure in space-time. Now, these are the ways chaos is generated. So there could be, we can show that random circuits or random unitaries can lead to chaos, but it remains open whether, what the relationship between random matrix theory or level spacing statistics is between that and our notion of chaos. More work to be done. I think there is a way to do it. Not quite sure how, but there must be a way to do it. This also allows us to put classical chaos and quantum chaos on the same footing. So you've heard, in first grade quantum mechanics that there is no notion of initial sensitivity to initial perturbation in quantum mechanics. That's false. There is. I won't talk about it here, so you'll have to. We have to do something during discussions. Yeah.
So when you mentioned volume law, do you mean that in this case there's no efficient MPO representation for the process tensors?
Yeah. The statement that we really use is that if you make any bipartition, the entropy should scale as the size of the small. But yeah, that also implies that there is no efficient MPO representation. And we don't want to make the bipartition strictly between space and time, because if you do that, it fails. And that's how Lindblad reached the wrong conclusion. And he was looking at dynamical entropy. And it turns out that Jordan Kotler has several papers showing that dynamical entropy is always extensive. But there are ways to get around it. It's quite interesting, still open. Okay. I've got 15 minutes. So I'm going to talk about complex processes. I don't really have a whole lot to say because folks here know way more about this than I do. But one of the motivations for me to get into this whole business was the idea of the FMO experiment. Right or wrong, it was at least inspiring. So imagine you have some system you want to study, it's strongly coupled to an environment. You could hit it with some ultra short light pulses and see its response. That is the language of process tensor. You've got the time scale of the environment is much larger than the time scale of the control, and then you can study it. And we were thinking about some interesting ways of reanalyzing this problem. Now let's go back to this idea of different structures, and one might ask that, do we get the same level of richness in entanglement in processes? And the answer is yes. You can find both say the G H Z and the W-type entanglement in a tripartite process. You can find just as much richness in a four-partite process. So you get genuine multipartite entanglement. That is a thing that happens. Now, if you have a process that doesn't have long-range entanglement, then you can Monte Carlo it, right? So that's like a direct result. Then you can just say that I only have to worry about a little chunk, and then I can get the next chunk without having to use up a huge amount of memory. All right, so then the question is, how complex can a quantum process be? So we have recently shown in this paper that they can be as hard as SAMP BQP. So SAMP BQP is potentially the same as BQP, the things quantum computers can do, but SAMP BQP is like when you're sampling from a quantum computer. So this is a kind of a cute version of Shor's algorithm. You can run Shor's algorithm on a single qubit and do some local processing. And this is nothing but a process tensor, right? So this process tensor has, it's well into BQP, at least we think, right? We don't think it can factor classically. We can also do random process sampling and look at the distribution. And so this is 5 time steps, 50 time steps, and I think this is 100 time steps. And what you see is a Porter-Thomas distributed outcome. And that means this is likely to be hard to sample from classically. So it's generating a distribution that's classically hard. So in other words, what we do is we take a process, you make a sigma Z measurement at every time step. You do nothing different, just, so that's related to the Google supremacy experiment, right? So processes can be hard. So there will be processes that classical methods will not be able to reach. It's just not going to happen. And that includes instances where you are looking at things like Nakajima-Swanzig master equation, because there you're just switching your sampling from, say, a sigma Z measurement to a Bell basis measurement. Right? So you're just making the measurement at every time step in psi plus. And that's going to be just as hard, right? There's just a local change in basis. So there will be, so that relates to one of the topics that Miles put up on the board yesterday. What's the role of quantum computers? Well, they're going to do something. They're going to have to do something because classical computers probably won't be able to get to some of these. This is just an advertisement. We're working on a Mera-inspired process. So there is still a lot more to be done. We can take the process tensor, turn it into something like a Mera, and then explore. This is, in particular, we want to do this to get to processes where you have power law correlation decay, power law non-Markovianity, and with this, we actually even see power law decay of quantum memory. So it's got full richness. So yeah, the line between what is quantum, what needs quantum resources and what needs classical resources remains blurry. All right, now this is the main talk that I promised, which I'll try to get through. So one of the applications of this process tensor is going to be in quantum computing. So let's say we have a quantum computer, we want to apply a sequence of gates. Normally, we assume that each gate is noisy on its own, and we can represent it as some map, some completely positive map. But why should the environment go away, right? I mean, it may not. So if it doesn't, then your second gate may depend on the first gate. So your errors are correlated in time. So you want to be able to characterize and correct that. And this is, we want to characterize and correct that without error correction, because in order to get to error correction, in order to get 1,000 qubits to work nicely with each other, you got to be able to do this. This was a preliminary experiment showing that it is non-Markovian. Now, what if you don't deal with it? you have some simple, say simple crosstalk, or maybe a simple coherent error or incoherent error. Those things will spread light cone, and it will lead to something highly complex. And then your error, so if you were to separate out your process, the stuff that you don't control from the quantum computation itself, the process will be as complex as the computation. And that's not good because you've got no way of talking about it, right? You need a quantum computer to talk about it. So you need to get rid of it. All right, so how do we do it? Well, okay, first we need to identify the mechanisms for error. So again, this is the process tensor. As we said that this is non-Markovian memory, but we also have a different notion of errors where the errors may exist in the control and may exist in the measurement. But we have different ways of dealing with that. So for instance, errors in control is dealt by gate set tomography, which is a state-of-the-art tool developed by Sandia folks. Non-Markovianity, I'll present a tool called process tensor tomography that is able to characterize non-Markovian noise in quantum computers. But then we have things like spillage errors that we don't really know how to talk about. In other words, every time you apply a control operation on your system, you also affect your environment. This happens naturally in continuous variable GKP encoding. And you get this mode entanglement that you don't quite know how to deal with. The gauge mode is called, as they call it. And then there's issues of terminating measurements, but one can apply noise mitigation techniques there. So what we have done in a paper that's coming up is we have packaged all of these things together into a single software that relies on some work that was done at Flatiron a couple of years ago and was just published recently. So let me talk about our first characterization. This was done on several IBM computers, and we got extremely high fidelity, only limited by shot noise. And to compare the reconstruction fidelity, and to show that we are actually accounting for something non-Markovian, we compared it to GST, and in non-Markovian regime, where we have some complex background, we tend to do much better. Of course, it's not a comparison. GST is really doing something amazing. It's doing tomography in a self-consistent way. Process tensor tomography is not self-consistent. We'd like to combine the two. The number of experiments you need to do this is 24 to power k, where k is the number of time steps. That's not great. So we'll deal with that. So the next idea was to develop a maximum likelihood characterization, and the results get better, and the 24 to power k becomes 10 to power k, so slightly better. So we're getting there. Here are some results. Again, they're mostly shot noise limited. Now, one might even ask, is there even non-Markovianity in these devices? And so we did this characterization, and from that characterization, we bounded the quantum non-Markovianity. So this is the quantum non-Markovianity. This is the quantum mutual information. So these are bounds on upper and lower bounds on non-Markovianity in these three-step processes. And you can see that it's there and it's sizable.
Sorry, Kavan, this is the QMI of what? Between what and what?
Sorry, say that again?
What, this is the QMI of between what and what?
Yeah, so you take the process tensor and you take its mutual information with respect to the marginals. So it's the relative entropy. So let's say you have a bipartite state, rho AB. Its relative entropy to its marginal is identical to the quantum mutual information. So we just call it quantum mutual information. It's probably a bad title.
I see.
You can also do it between some left part of the process or future of the process and the past of the process. That is a measure of correlations. So that's a way of non-Markovianity. If you do it over multiple time steps, then it's the relative entropy. Negativity is just you do some transpose with respect to the process tensor. So that's the entanglement. So it is genuinely quantum. And in fact, we can find genuinely multipartite quantum entanglement in some of these things. This was engineered, but it can exist. Okay. We also employed classical shadow tomography to characterize huge processes. These are 20-step processes. You can't write down the whole 20-step process, but you can take any 1, 2, 3, 4 time marginal from that. You can get that out of the data. You can get extremely high fidelities for all of these. You can compute non-Markovianity and various other things. So it just comes out of the data. So it's the process tensor tomography plus shadow tomography. And what's interesting is that the usual ways of talking about non-Markovianity will tell you that it goes to 0 after some time steps, after a few time steps. But in fact, when you look at the negativity and QMI, multi-time non-Markovianity, it remains sizable through and through. So it somehow reaches equilibrium with memory. This I'll just briefly mention. You can use the same ideas and the causal structure of processes to identify crosstalk versus non-Markovianity. So imagine 2 qubits are talking to each other. They could be talking to each other directly, or they could be talking to each other by impurity. How do you know? We can figure that out just by some classical shadow filtering. Without going into details, what's nice about the whole program is that it allows you to incorporate the usual tools like, shadow tomography, maximum likelihood, GST, all of that, because it's just a multi-time completely positive map, right? So the usual tools just need a little bit of manipulation to make it work. Okay, so let's make it self-consistent. I think I have no time, so I'm just gonna say that it can be done using how it can be done, never mind, but we use the work by Torlai, and that's actually similar to something that we did in 2020. We did it multi-time, they did it multi-state, and we can do a self-consistent, i.e. Combine make non-Markovian GST. That is easily do, and this uses tensor network, and we can check, does it work? We can check standard process tomography versus self-process tomography. It works better, right? It converges better. Look at the scale here and the scale here. It's much better. We can compare correlated environment, correlated control versus not correlated control, blah, blah, blah. We can make it all work. This is data from IBM where we have 1 qubit over 18 time steps, 2 qubit over 9 time steps, and so on. So this can be done in space-time. And in the next step, what we want to do is bring up the notion of Markov order so you can characterize small chunks and piece them together. Now, I don't have any time, but I just want to say one more thing. Why do you care to characterize anything? And the reason is you can control things. So here's data where we use characterization. And so if you don't do optimal control based on characterization, the machine fidelity has a massive variance and a terrible mean of 75. We can pump that up to 92% fidelity with a mean of 0.02. So characterization means better control. And this requires multi-time correlations. This requires the process tensor. There are other ways of doing it too, but it requires. Okay, I'll just stop. I do want to say one last thing, that the goal is to put this together into Pigsty, which is the software package by Sandia. That'll happen soon. By the way, I should really plug Greg White, who's done all of these experiments, an amazing student, moving on to Berlin, but he's the mastermind behind all of the experiments and characterization. Sorry for going over time. Thank you.
All right, I have a question.
for the nice talk. So on the tomography, where you have the scaling with 10 to the power k, can you do better if you make an assumption where you say, okay, I have a maximum time of entanglement over time, and I have a process which doesn't change, the fundamental Hamiltonian doesn't change over time, and then do something.
It doesn't, you don't even have to make that assumption. You can, so the idea of Markov order is the length of the memory. And so what you need to do is you can construct a block of some memory length, and then you can construct the next block, and you can reduce 24 to the k. You can bring that k down, and because this is, L is a constant now. And in fact, these are different choices of L. This is green is L3, orange is L2, this is L1.
Okay.
It progressively gets better.
That the underlying total Hamiltonian would be constant over time, so it does not require that.
Potentially, but it's easy enough to just characterize these small process tensors, stitch them together. This stitching is, by the way, Greg thought of this. I have no idea how, because it makes no sense to me, but it works. So.
Yeah, thank you.
Regarding the quantum chaos, if I consider process tensors where the unitaries have only support in the environment, if I find sub-volume law entanglement, does that mean that I have an integrable environment, basically, or?
Wait, so if the system is not interacting with the unitary, then no. So if the butterflies, no.
Sorry, let's say I do a trotterization in the system path evolution, and then I construct the process tensor in such a way that there is I guess there will be overlap between some interaction in the process tensor between the system and the environment, right?
Yeah.
Okay.
Has to be. But there is you could have situations where it's non-chaotic for some time, and then it becomes chaotic in a large time limit, which is, put a little bit of cream in your coffee and it'll retain pattern for a bit, but then it'll be gone.
I guess I'm asking because some people think that at least for, like, say, non-interacting electronic paths, that the temporal entanglement is sub-volume law. So
it's a different notion of temporal entanglement. This is one of the things that I would, if you're working on that, I would love to talk, because it is a different notion. It's very related. What they do is they take the temporal process tensor and cut it in half.
Is it like a folding thing, or?
The folding thing is already done here because we work in the Louisville picture. But it's the time slice they consider is just the process tensor. They cut that in half. We keep this environment around, so it's interesting. But those results are really fascinating because they're in contrast with Kotler's result, where everything is volumetric, seemingly, right? So something is cool there.
But now, with regard to what you just said, in a classical, in a classical system, you are either in a regular portion of phase space or in a chaotic one. You don't just evolve from one to the other.
Yes, well, maybe, right? Because there must be intermediate regimes, right? So, like, again, putting a little bit of cream in coffee, you're going to retain some patterns, but it will eventually diffuse. So,
But I mean, in the KM theorem, you are either, if you're in a torus, you stay on the torus, and if you're not, you don't go to the torus.
yes, I don't know how to bring the mathematics in alignment with my intuition. So something is funny. I don't know the answer to that, but I imagine it is a similar issue here. There is one subtlety that that was pointed out by Emerson in about 20 years ago, along with Seth Lloyd and some people. Quantum perturbation. So if you do like Perez-Loschmidt-Taco type of thing, you have way more perturbations that you can make. So if you make arbitrary perturbations, you will break integrability. You have to be extremely careful with your perturbations in order to remain integrable. So this is why there is a slight difference. So you can get out. So if you start with an integrable system, you make a very small perturbation, but if it's breaking integrability, it will lead to chaos eventually. Maybe slow, but it'll happen.
But the structures are there, so the structures are time independent in phase space.
It's no phase space, right? So
Yeah,
it's a different notion.
so it's
Yeah.
different.
Yeah, so I think there's still more more things to think about there. Yeah.